Somewhere in a laboratory in China right now, an engineer is stirring a pinch of the thinnest material ever discovered into an ordinary bucket of concrete. Not a scoop, not a handful, a pinch so small it barely registers on a scale, roughly 0.005 of 1% of the total mix. And yet that microscopic addition makes the concrete tens of percent stronger, harder to crack, far more resistant to water, and strangest of all, gives it something concrete has never had before, the ability to feel the weight pressing down on it. This isn't a lab curiosity you'll never see again. Concrete is the second most used substance on Earth, right after water. So even a small improvement, multiplied across every bridge, tower, and highway humanity builds, becomes one of the quietest and biggest revolutions in construction history. So let's separate what's real here from what's hype, because in this story, both are very much mixed together. To understand graphene concrete, you first need to understand graphene itself, and why, for 2 decades, it was one of the most overhyped materials on the planet. Graphene is a single layer of carbon atoms locked together in a hexagonal pattern that looks like chicken wire. That's the entire material. It's exactly 1 atom thick, making it the thinnest material ever isolated, so thin that scientists describe it as 2-dimensional. And that impossibly thin sheet carries properties that sound pulled from science fiction. It's stronger than steel by a wide margin, with a tensile strength measured around 130 gigapascals, making it one of the strongest materials ever tested. It conducts electricity better than copper, conducts heat better than almost anything known, stays flexible, is nearly transparent, and is so tightly sealed that even helium atoms can't squeeze through it. When 2 researchers at the University of Manchester first isolated graphene in 2004, using nothing more exotic than a lump of graphite and ordinary sticky tape to peel it down to a single atomic layer, the discovery won a Nobel Prize and set off 2 decades of bold predictions about how graphene would transform everything. Bendable phones, extraordinary batteries, filters that could pull salt straight out of seawater, computer chips 1,000 times faster than what we had. The list of promised miracles seemed endless. And then, for the most part, none of it arrived. Not because the science was wrong, the properties are completely real, but because of one stubborn, unglamorous problem. Making the stuff was absurdly expensive. For years, high-quality graphene cost somewhere between $67,000 and $200,000 per ton. At that price, you're not building bridges with it. You're barely building anything at all. Graphene became the material perpetually stuck in tomorrow, dazzling in the lab and completely absent from the real world. Material scientists joked that graphene could do anything except leave the laboratory. But concrete changes that equation entirely, and here's why. You don't need to build an entire structure out of pure graphene. You only need to sprinkle a microscopic amount into a material we already pour by the billions of tons every year. And when you do that, when graphene meets cement, something remarkable happens at a scale far too small for the human eye to see. Here's the puzzle worth sitting with for a second. How can a dusting of carbon powder, making up a tiny fraction of 1% of a concrete mix, transform an entire batch? The answer lives in the microstructure, at the level where concrete is actually formed. When cement and water are mixed together, a chemical reaction called hydration begins, growing a tangled network of crystals that binds everything into a solid mass as the concrete cures and hardens. But that process is messy and imperfect. It leaves behind microscopic voids, weak points, and tiny pores scattered throughout the material. Those flaws are exactly where cracks begin, and where water eventually seeps in to start the slow decay that destroys concrete over decades. At the microscopic level, ordinary concrete is riddled with gaps. There's also the matter of sheer surface area. Because graphene is only 1 atom thick, a single gram of it can unfold to cover an astonishing amount of space, thousands of square meters. That means even a microscopic mass of graphene reaches an enormous share of the cement it's mixed into. This is the quiet secret behind how such a tiny pinch can do so much. You're not really adding a small amount of material, you're threading an almost unimaginable amount of surface area throughout the entire mixture. Graphene attacks the flaw problem on several fronts at once. First, those atom-thin sheets act as nucleation sites, essentially seeds around which the cement crystals grow. Instead of forming a loose, disorganized tangle, the hydration products grow denser and more orderly around the graphene, producing a tighter microstructure with fewer voids. Chinese researchers examining this process under electron microscopes documented exactly that outcome, finding that graphene-modified concrete developed a denser structure with noticeably enhanced formation of hydration products compared to conventional concrete. It's worth mentioning that engineers work with several close relatives of graphene here, including graphene nanoplatelets, which are tiny stacks of a few graphene layers, and graphene oxide, a version studded with oxygen groups that blends more easily into water. Each behaves slightly differently, but the core effect stays consistent. The material simply cures better. Second, graphene bridges cracks. Because those sheets are extraordinarily strong and spread throughout the mixture, when a microscopic crack tries to form and grow, it runs straight into a three-dimensional network of graphene that disperses the stress and stops the crack before it can spread. The fracture gets caught at its earliest possible stage. And third, that same layered, interlocking structure creates a barrier against water. Graphene sheets stack and overlap inside the mixture, forming a maze that water struggles to penetrate, with studies reporting improvements in impermeability of over 35%. One Chinese study found that adding graphene cut the maximum depth of water penetration by a striking amount. And because water can't get in as easily, the concrete resists corrosion, resists spalling, and avoids the slow deterioration that eventually kills conventional structures. Denser curing, crack bridging, and waterproofing, three separate effects from one ingredient, all operating at a scale measured in billionths of a meter. Now let's talk honestly about how much stronger this actually makes concrete, because this is exactly where online headlines tend to start exaggerating. The research itself is real and genuinely impressive, but the numbers shift quite a bit depending on the type of graphene used, the dose, and the mix design. So instead of quoting one dramatic figure, here's the honest range drawn from actual published studies. A 2025 study on graphene nanoplatelet reinforced concrete reported compressive strength increasing by up to 40%, tensile strength rising by 27%, and toughness improving by 47%. A separate Chinese study on multifunctional graphene concrete, also published in 2025, measured a 44% increase in compressive strength. Broader reviews looking across multiple graphene cement studies found flexural strength, meaning resistance to bending, improved by anywhere from 41 to 59%, with compressive strength gains ranging between 15 and 33%. And notably, some of the most efficient results came from remarkably tiny doses. One study achieved a 23% boost in compressive strength and a 31% gain in another property using just 0.05% of graphene relative to the cement's weight. Another study found that even a minute addition of 0.1% produced solid double-digit improvements across multiple properties at once. These gains stack further when graphene is combined with other reinforcing materials. A 2026 study found that pairing a small dose of graphene nanoplatelets with polyvinyl alcohol fibers pushed compressive strength up by nearly 44%, split tensile strength up around 22%, and flexural strength up over 22%, all while simultaneously improving impact resistance. Graphene has also shown particular promise in cutting-edge techniques like three-dimensional concrete printing, where a graphene-enhanced calcined clay mixture is being explored for printed housing, exactly the kind of low-cement, high-performance blend that 3D construction demands. So what's the honest takeaway here? Graphene doesn't make concrete 5 times stronger, whatever a dramatic headline might claim. What it reliably does, across dozens of independent studies, is improve strength by roughly a fifth to a half, sharply increase toughness and crack resistance, and dramatically boost durability and water resistance, all from an almost invisible amount of additive. That's not a minor tweak. On a material produced at a scale of billions of tons every year, an improvement of 30 or 40% is enormous. But it's an enhancement to concrete, not a replacement for basic physics, and anyone claiming otherwise is selling something. And here's the part that might be even more interesting than the strength gains. When you fill concrete with a material that conducts electricity, the concrete itself gains an entirely new sense. This sounds like science fiction, but it's completely real. Graphene is an outstanding electrical conductor. Ordinary concrete, by contrast, is essentially an insulator. But mix enough graphene through the material, and you create conductive pathways running throughout the entire structure, turning a passive slab of building material into something closer to a sensor. Here's how it works. When a load presses down on graphene-infused concrete, a truck rolling across a bridge, a crowd gathering on a floor, the ground shifting beneath a foundation, the material deforms very slightly. That microscopic deformation changes how easily electricity flows through the graphene network, altering the concrete's electrical resistance in a way that can be precisely measured. Measure that resistance, and you can read the stress. The concrete, in effect, feels the weight resting on it and converts that feeling into a readable signal. Engineers call this self-sensing or smart concrete, and the implications are genuinely significant. Picture a bridge that continuously reports on its own structural condition, capable of signaling in real time that a support is carrying more load than it should, or that a hairline fracture is forming deep inside a beam, years before a human inspector could ever detect it. Picture a building that senses the strain of an earthquake as it happens, or a highway that counts and weighs the traffic passing over it purely from the electrical signal running through the road surface. Instead of sending inspectors out to visually check for cracks and tap on surfaces with hammers, which remains a genuine part of infrastructure inspection even in 2026, the structure monitors itself continuously from the inside. For a country building bridges, tunnels, high-speed rail lines, and skyscrapers at the pace China does, self-monitoring infrastructure isn't a gimmick. It's a way to catch failures before they become disasters, to schedule maintenance according to a structure's actual condition rather than a guess based on a calendar, and to make massive public works safer across their entire lifespan. There's a bigger shift buried inside this idea. For its entire history, concrete has been silent. You pour it, it hardens, and it endures quietly until, one day, it doesn't, and by then it's often too late. Self-sensing concrete ends that silence. The structure becomes a continuous source of data about its own condition, feeding directly into the digital monitoring systems that modern infrastructure increasingly depends on. A material that carries data as well as weight is a fundamentally different category of building material. But none of this matters if you can't actually afford to produce the graphene in the first place, which is exactly the wall this entire field kept running into. And that wall is where a genuinely clever solution comes in, turning trash into treasure. Remember that graphene has historically cost up to $200,000 a ton. That single fact is what kept graphene concrete trapped in research labs for years. So the real breakthrough here isn't just the concrete itself, it's a radically cheaper way to produce the graphene, and it involves turning garbage into one of the most valuable materials on Earth. The technique is called flash joule heating, pioneered at Rice University, and it's almost comically simple in concept. You take nearly any material that contains carbon, coal, food waste, old plastic bottles, used coffee grounds, discarded tires, and blast it with a massive jolt of electricity for a tiny fraction of a second, heating it to around 3000 Kelvin, roughly 5000 degrees Fahrenheit, in about 10 milliseconds. Everything that isn't carbon boils off as gas, and the remaining carbon atoms rearrange themselves almost instantly into graphene. In the blink of an eye, trash becomes one of the most valuable materials on the planet. The economics here are remarkable. This flash process can convert a ton of coal or waste into graphene for a small fraction of the cost of traditional production methods. To put the raw material difference into perspective, the graphite feedstock used in older methods can cost anywhere from $1,000 to $3,500 a ton, while coal costs around $25 a ton. The researchers behind this technique made a point worth sitting with, especially given who we're discussing. This process could give coal an entirely new purpose by converting it cheaply into a much higher value building material. China burns more coal than any other nation on Earth, meaning it already has the feedstock, the waste streams, and the manufacturing scale needed to produce cheap graphene at an industrial level, precisely the bottleneck that has held this technology back everywhere else. And the idea gets even more clever from there. One approach uses flash heating to convert coal-derived coke into a graphene aggregate that replaces the sand and stone typically used in concrete entirely, producing concrete that's 25% lighter while gaining meaningful improvements in toughness and strength. Why does that matter so much? Because the world is quietly running out of construction-grade sand. We're extracting it faster than nature can replenish it, and a genuine global sand shortage is on the horizon. A process that converts cheap coal waste into a viable sand substitute doesn't just make concrete better, it could help sidestep an entire resource crisis before it fully arrives. Turning waste into a supermaterial is exactly the kind of resourceful, vertically integrated approach that plays to China's industrial strengths. This flash technique is already being commercialized. A company spun out of the original research is working to scale it up, and the underlying chemistry is simple enough that it could be reproduced industrially by anyone with access to cheap carbon and sufficient electricity. That last detail matters, because it means the advantage flows toward whoever controls the most feedstock and the most manufacturing capacity. So the strength gains are real, the smart sensing capability is real, and the cost problem finally has a workable answer. Which brings us to the piece that may matter most of all on a warming planet, what this technology could do to concrete's enormous carbon footprint. Here's a statistic worth sitting with. The production of cement, the binding ingredient that holds concrete together, is responsible for as much as 8% of all human-caused carbon dioxide emissions every single year. If the global cement industry were its own country, it would rank as the third largest carbon emitter on the planet, trailing only China and the United States. Concrete built the modern world, and in the process, it's been quietly cooking the atmosphere. Roughly speaking, for every ton of cement produced, nearly a ton of carbon dioxide is released into the sky, a consequence both of the chemistry involved and the intense heat required to fire cement kilns. The core problem is that most attempts to shrink concrete's carbon footprint involve using less cement, and using less cement usually makes the concrete weaker. The traditional workaround has been to blend in supplementary materials like fly, ash, or slag, industrial byproducts that can partially replace cement, but those substitutes come with their own limits. Fly ash tends to cap out around a third of total cement content before it starts hurting workability and finish, and slag rarely goes beyond half before durability begins to suffer. It's historically been a brutal trade-off. You could have a greener mix or a stronger mix, but rarely both at once. This is where graphene flips the equation. Because graphene makes concrete significantly stronger per unit of cement, engineers can use noticeably less cement while maintaining the same structural performance. Less cement means less carbon, without the usual penalty of a weaker structure. The numbers here are genuinely compelling. Studies on graphene nanoplatelet concrete have demonstrated substantial potential reductions in carbon dioxide emissions by allowing cement content to be cut significantly. One estimate suggested that a concentration of as little as 0.1% of flash-produced graphene in cement could reduce concrete's overall environmental impact by roughly a third. And when the graphene itself is produced from waste carbon, food scraps, and plastic that would otherwise rot in a landfill and release methane, you get a genuine double benefit. You trap carbon that would have become greenhouse gas, and you use it to shrink the carbon footprint of cement production at the same time. It's one of the rare environmental stories where the accounting works in your favor twice over. For China, which pours more concrete in some years than the rest of the world combined, and which has committed to reaching carbon neutrality by 2060, a stronger concrete that requires less cement isn't a nice bonus, it's a strategic necessity. Chinese materials scientists have explicitly flagged low-carbon, long-life, ultra-high-performance concrete as a national research priority for precisely this reason, and graphene sits right at the center of that goal. So this all sounds remarkable. Stronger, smarter, cheaper, and greener all at once. Which means it's time for the part that separates an honest breakdown from a pure hype video, because graphene concrete still has real problems standing between the research lab and the skyline. The first and biggest issue is dispersion. Graphene's advantages only appear if its sheets are spread evenly throughout the concrete, but graphene naturally tends to clump together. The sheets stick to each other, forming clusters that do nothing useful and can even create new weak points. Getting a tiny quantity of graphene to disperse uniformly through a churning mix of cement, sand, water, and gravel is genuinely difficult, and getting it wrong can erase the strength gains entirely. This is also exactly why published research numbers vary so widely. Different dispersion methods produce dramatically different results, which makes it hard to write one reliable recipe that works consistently on a real construction site rather than inside a controlled laboratory. Labs typically rely on ultrasonic baths and chemical surfactants to break apart clumps and separate the sheets, tools you can't easily bring to a highway job site on a rainy afternoon. Closing that gap between laboratory beaker and cement truck remains one of the central unsolved challenges in the entire field. Second, there's the issue of cost and scale. Flash-produced graphene is a genuine breakthrough, but it's still mostly proving itself at gram and kilogram quantities in research settings. Scaling that up into the millions of tons of consistent, affordable graphene a real construction industry would need is an enormous manufacturing challenge that hasn't been fully solved yet. Prices are falling quickly, but they haven't hit rock bottom, and quality still varies significantly between suppliers. Third, there's the matter of standards and building codes. You simply cannot construct a bridge using a material that no regulatory body has formally approved. Graphene concrete doesn't yet have the mature, internationally agreed upon standards and long-term performance data that engineers and regulators require before trusting a new material with human lives. Concrete that's only been studied for a handful of years can't yet prove it will still be standing, uncracked, 80 years from now. That kind of testing takes real time, and there's no shortcut around it. Materials simply have to be watched as they age. Regulators, quite reasonably, don't grant approvals based on one promising afternoon in a lab. And fourth, there's a reproducibility gap. Because results depend so heavily on the specific type of graphene used, the dosage, and the mixing method, one lab's impressive 44% gain can become another team's disappointing single-digit improvement. Until the industry settles on consistent, standardized processes, graphene concrete will likely remain more promising than proven for large-scale, load-bearing structures. None of this erases what's been achieved here. It simply means this technology is still in the middle of its climb, not yet at the summit. A genuinely powerful tool that's real, advancing quickly, and not yet ready to replace every pore on every job site. So step back and take in the full picture. A material 1 atom thick, stronger than steel. Once so expensive, it was effectively locked out of the real world, now being sprinkled in tiny traces into the most heavily used building material on the planet. Concrete that cures denser, cracks less, and resists water far better than before. Concrete that can feel the weight bearing down on it and report its own condition from the inside. Graphene conjured cheaply out of coal, trash, and waste, sidestepping both a looming cost crisis and a coming sand shortage at the same time, while offering a genuine path toward cutting the staggering carbon footprint of cement by using dramatically less of it. Ordinary concrete has held up civilization for 2,000 years by being cheap, strong, and brittle. This new generation is aiming to be cheap, far stronger, self-aware, and cleaner all at once. And the country pouring more concrete than anyone else on Earth is racing to figure out how to make it at scale. It won't happen overnight, and the hype is still running well ahead of the actual concrete being poured. But if even half of what these laboratories are demonstrating holds up, once it reaches the real world, the humble gray material sitting beneath every city on the planet is about to get a great deal smarter. And that shift would transform construction the same way concrete itself once did. Quietly, invisibly, and completely. Not with a bang, but one atom-thin sheet at a time.